One. Hi, everybody. Welcome to week number 8. It's Mr. Harfness with Ms. Ashburn and Ms. O'Reilly. I hope this video is finding you well as we head into Memorial Day weekend. We're in the home stretch now, so all it is downhill into June. So we're almost there. But before we go, kind of good segue, we're going to talk about a lot of explosions today. We're going to talk a little bit about the differences between nuclear fission and nuclear fusion. It's really important as far as why does this concern you. Nuclear fission is really big because you live in a town that has a power plant. We also get a lot of energy from fusion from a star. So all those things are really important to us, and we hope that you can walk away with some real life application to today's lesson. Like everything else in this unit has been a lot of real life application. So I'm going to throw it to Miss Ashburn.
I was gonna say, I lost track. There we go. All right, so nuclear fission. So fission is the splitting of the atoms. And what happens is a nuclei basically hits and then causes the nucleus to basically break up. And you have what are called decay particles. And depending on what isotope is decaying will depend on then what particles are made. And you notice one of the byproducts is energy. All right, so we can run in the nuclear power plant, you're going to run a controlled reaction. And here they're showing the U-235. It's getting bombarded by a neutron, right? And then you are going to break up, and you've got energy. You see the krypton 91, the barium 142, and 3 other neutrons. So those are the decay particles as a result of this reaction.
So nuclear fission causes a chain reaction. That means that more neutrons are released. So you saw in the last slide that part of what initiated the reaction was the neutron bombarding the original isotope. And then as a product, there were 3 neutrons that were released. So when those more neutrons are released, they strike nuclei of other isotopes and creates a domino effect or a chain reaction. Because of this, these are usually very large and not as stable. Nuclear power stations use that heat that's released, that product, by the nuclear reaction to boil water and make steam. And that steam then turns turbines and creates the energy, which you're going to see later. This is a diagram that shows that chain reaction. You can see that when this first neutron hits this initial nucleus, 2 neutrons are formed. And then when this neutron hits this nucleus, 2 more are formed, and each one forms 2 more. So you can see how it's growing exponentially. And this is the chain reaction.
Okay, now we're going to talk about, though, how this plays out for producing electricity for us. Now, in our area, we're very familiar with this because many of you probably have family members that work at Dominion, at the nuclear power plant. So currently there are about 103 nuclear power plants in the United States and about 435 worldwide. France and Japan are really the leading countries in nuclear energy. Japan, because of Fukushima, obviously have had some setbacks, but they really were the forerunners in looking at the advancements of nuclear energy for power. 17% of the world's energy comes from nuclear. And here you're looking at the different countries. So you see France in the number 1 at 75% is nuclear energy. And down US, we've got about 20% is nuclear energy. And now what we're going to do is go on. We're going to talk a little about how that works. Here, what we're going to talk about is what's called a light water reactor, which is what Dominion is. Interesting enough, there are different types of nuclear reactors. I'm going to kind of walk you through some of them. So you have 2 types of rods in your core. And one of them are fuel rods, which makes sense. We need the fuel, and that's your uranium. All right. And then you have what are called control rods. And these control rods can be lifted up and down. And their job is to control the chain reactions. And I'm going to talk about that in a minute. The third thing I want to talk about is what's called the coolant. And the coolant and moderator, basically their jobs are to absorb the heat, but also to get the neutrons at the right speed, which is interesting. For this bombardment to happen, for the decay and the reaction to take place, neutrons have to actually be at a specific speed. So you have a moderator kind of gets the neutrons at the right speed. Your control rods absorb the extra neutrons. So you know how we showed in the previous slide how the chain reaction happens? Well, you don't want that in a nuclear power plant, right? You only want so much energy being produced at any one time. So you want to control how many reactions happen. So the control rods kind of take some of the extra neutrons out of the game. So only so many reactions take place and only so much energy is produced. And that energy, though, gets absorbed by the water. And it's under a lot of pressure, so it doesn't boil, right? But then it's going to go and it actually heats up other water. And that other water is allowed to boil. And that steam, you can see the steam generator, that steam then goes up, turns a turbine to generate the electricity. And then there is a third kind of circle or ring of water, and that comes from the outside. It absorbs extra heat, kind of cools it off before it's sent all the way back, right? It transfers the heat into the steam generator. So basically, you are boiling water. This is one way we boil water. Coal plants do it the same way. So how we make electricity is very similar. It's the fuel source that is different, and here it's a nuclear reaction.
But sometimes, but sometimes there's nuclear explosions. These explosions occur when the reaction is allowed to run out of control. So you saw in the last slide, there was a lot of different ways to catch and protect the reaction from getting too large. But sometimes it does run out of control, and when that large amounts of energy is released very quickly, you have a nuclear explosion. So the nuclear reactor, controls the rate of the energy release. And there's uranium oxide that's held in the fuel rods. That's that uranium that we are using as our fuel. Those rods are lowered into the reactor core. There's a coolant, which is the water that you saw, circulated to remove the heat. The control rods are going to absorb those extra neutrons, and they're going to control the rate of the chain reaction. So you can move that up and down. You can raise it to speed it up and lower it to slow it down. And here's just a zoomed in look of just that nuclear reactor here.
And you have to remember that it's not a nuclear explosion, right? There's not enough uranium. It's the heat. The energy release causes what's called a meltdown, and you end up with either a hydrogen, because hydrogen's released, or you end up with a steam explosion because it's melted down basically to the groundwater.
And to wrap it all up, the last little slide here is on a process called nuclear fusion. You have to kind of think about when you fuse things together, you're taking two pieces or two parts and you're combining them into one. In the case of fusion, we're taking two small nuclei and we're going to kind of put them together or combine them to create a nucleus of greater mass. So basically, we're going to end up with if you look towards the bottom of the slide, you see we start off with 4 hydrogen atoms. And then this is a very simplistic diagram. This is a multi-step process, but at the very end, we end up with taking those 4 hydrogen atoms and combining them to form 1 helium atom. So how does this happen, or where does this happen? The place where it happens the most is in stars. A star doesn't become a star until it actually can do the process of nuclear fusion. The process of literally taking hydrogen and forming it into helium. We don't really think of the sun as being a helium maker, but that's what it does. It literally will take all the fuel that it has, which is a lot of hydrogen, and be able to convert it all to helium. Now, in our sun, which is a medium-sized star, the core temperature is between 15 and 17 million degrees Celsius. So nuclear fusion takes place at a little bit faster rate than if it was at 10 million. When you hear of big stars that might make a supernova, you're talking about maybe 40 to 50 million degrees Celsius is their process of nuclear fusion. So the warmer it is, the faster the fusion process goes. And ultimately, what happens with a star like ours, it uses up all its hydrogen and eventually it turns into helium. And our star is going to die a very slow, very not big explosive death. This is kind of going to be, it's going to get bigger first because it turns into a red giant. when it runs out of hydrogen. And it kind of expands and expands and expands, trying a last ditch effort to kind of use its fuel up. And then after it does that, which it doesn't take very long for it to do, it will actually shrink and shrink and shrink, and it'll turn into a white dwarf. And just like one day, like a light bulb goes out, our star will go out. So the temperatures are not high enough to create a huge, huge, huge supernova. And that's not going to happen here. How has this been affected on Earth? Well, you've all probably have heard of the hydrogen bomb. It goes back into the Manhattan Project into the late 30s, early 40s, and eventually with the dropping of the atomic bomb in Japan, both of them in 1945. So that is a man-made example of nuclear fusion, whereas the more natural process is going to be in stars. Now, the second bullet, which I skipped before, is that this releases a lot more energy than fission. Fusion produces a lot more because you're literally combining two nuclei together. So the way that I remember it is that fusion is to make and fission is to break. Very old school method, but fusion, you put things together, fission, you take things apart. And that, in a nutshell, is our short video on fission and fusion. So we hope that you've had a good week. And as always, if you have any questions, you can contact us via email or Google Classroom, and we will get back to you. Hope all is well, and have a good weekend.
Bye, have a good week.
Bye, guys.